Starting a new course today, Dynamics of the Tropical Atmosphere and Oceans, a nice new book that just came out by Peter Webster of the Georgia Institute of Technology. He's a very well-known tropical climate person, has done tons of work in atmosphere ocean dynamics, monsoon especially, lots of observational work, lots of theoretical work, and lots of prediction work that he loves to do for floods over Bangladesh, Pakistan regions, and so on. Very good at statistics as well. The book consists of 18 chapters with final conclusion notes that is rather brief, so we'll go through those. I won't read through all of these, but you can see it includes a range of topics that are very fun and important. When you do a course as a semester, you try to pick and choose and have a theme that probably will not include all the chapters, but since this is a YouTube channel, I'm going to go through all the chapters and leave podcasts on all of them. And then obviously when you or I do a course, we are going to pick a subset of these to suit the purpose at hand. Climatology of the tropical atmosphere and upper ocean is the first chapter that I will start with. The book actually has a brief introduction to the history of how weather, meteorology, and climate evolved in terms of going back to Halley's first attempt at explaining Hadley cell in terms of westward moving sun and the heating that he imagined, which would create a longitudinal pressure gradient and drive a trade wind circulation, which turned out to be not so accurate. But Hadley in the 1700s, 1735 I think, did a remarkable job of explaining it in terms of a cell, equator to pole cell, just based on interpreting the winds in the lower latitudes from ships, and the terminology trade winds came up. The interpretation has been that trade winds related somehow to commerce and the ships plying goods and services, but Philander argues that that may have actually come from tread, T-R-E-A-D, which in sailing terminology apparently means the progress that a sailing ship makes. You also probably heard a phrase in good tread and so on and so forth. Nonetheless, there are other big events like the Challenger expedition, which doesn't come up so much in this book, but is critical for oceanographers. The equations of motion early on in 1904, I think, by Papa Bjerknes, who I think is Wilhelm Bjerknes. We will talk about Jakob Bjerknes, the son, who is very similar work in ENSO, made a huge dent in the way we think about ENSO today, El Nino Southern Oscillation. Walker in the late 1800s and 1900s looked at pressure and tried to explain monsoon droughts over India, famines, and created the so-called Southern Oscillation as a pressure variation between Tahiti and Darwin. There are Eric Eadie, Rossby, Jules Charney, Henry Stommel in oceanography, Walter Monk, and there are many characters and programs like the Global Atmospheric Research Program, which ran from 1967 to about 1981 or 82, I think. Within GARP, there was a global GARP Atlantic Tropical Experiment called GATE, and then there was TOGA, Tropical Ocean Global Atmosphere Program, which established the Tropical Atmosphere Ocean Array, which is now the key backbone of ENSO prediction system. We have since had Rama mooring system in the Indian Ocean, Pirata in the Atlantic Ocean, and so on. So I won't go through all the critical papers like by Matsuno and so on, Madden Julian and various other people who established Findlater, There are many Indian names that were also critical in discovering the Findlater jet, which is called Somali jet now, and so on. Okay, I think Dr. Koteshwara was the person who discovered that, and so on. So let's look at climatology of the tropical atmosphere and upper ocean to start the chapter and the course. I think you're all fairly familiar with this level of math, where if you look at any climate variable alpha as a function of let's say longitude, latitude, height and time, to get the longitudinal mean latitudinal depth section in the ocean or the atmosphere, height or depth and time, you would integrate along all longitudes, and if you want to just take out time as well, then you would integrate in time and produce a mean over longitude, latitude and height. Overall, when you want to look at zonal mean meridional section climatologies, it's easier to just integrate longitude and time out and create alpha bar as a function of latitude and height, which are depth in the ocean. In the ocean, we don't do this too often because the ocean has boundaries, right? There are different oceans, Pacific, Atlantic, Indian Oceans. You can look at zonal mean sections for meridional circulations, but for the atmosphere it makes much more sense because it's a global phenomenon, and it's dynamically much easier to look at the zonal mean meridional sections in the atmosphere to understand the basic processes of transporting energy from the low latitudes to the polar latitudes to balance for the energy excess in the low latitudes and energy deficit at high latitudes, which you would have learned in your basic climate course, or you can look at my other lectures on introduction to climate and so on my channel. Okay, so let's jump right into it with this example of sea surface temperature latitudinal distribution. Longitudes have been averaged integrated out, so you are going from 45 south to 45 north, which is enough for our tropical climate, atmosphere, ocean dynamics. There are extratropical, tropical interactions and feedbacks which we will address, but treat the extratropics as a forcing on the tropics and tropics as feeding back to the extratropics. So you are looking at temperatures in degrees centigrade, and you can see the maximum here in the zonal mean sense are in the range of 28 or so, and there is hemispheric asymmetry and seasonal asymmetry as well. So if you look at the red line here, which is for June, July, August, Peter calls these as the solstitial seasons, where you have the summer and winter solstices involved in these and time averages of December, January, February. You can think of as seasons, boreal winter and boreal summer seasons, and vice versa for the southern hemisphere. So the northern hemisphere is warmer than the southern hemisphere. You can see in the corresponding summers, and there is asymmetry at 45 degree latitudes as well because of the land-ocean distribution differences, and we will see later on that ocean transports heat against the hemispheric temperature gradient because it's mechanically forced to do that by the atmosphere, and the atmosphere then creates this energy equator, or the intertropical convergence zone, which moves energy across the equator back into the southern hemisphere. So the ocean is moving from energy from the southern hemisphere into the northern hemisphere through the meridional overturning circulation, and the ITCZ moves energy back across the equator to the southern hemisphere. The other little kink we have to note, of course, is that on the equator the temperature is not maximum. There is upwelling in the Pacific and Atlantic Oceans and Western Indian Ocean. So in the Pacific and Atlantic it's in the eastern tropical regions. In the Indian Ocean is the other way because of monsoonal circulation. So the maximum SSTs in fact occur off the equator in both hemispheres, with again difference in the maximum temperature. So we'll look at those sorts of details. Let me stop this here for a start, and then start getting into more specific atmospheric quantities in the same zonal mean meridional climatologies, and then we will start pulling it out like an accordion and look at other features, timescales, winds, and precipitation, and so on. Okay.